So I will in particular try to make the connection with the local conjectures we saw this morning, and in particular the conjecture about the L2 spectrum. But let me, so here K will be a global field through the talk. And I will start with an example, a very important example actually, and then we'll try to see how to go from this example to a more general situation. So which is the Ichino-Ikeda conjecture, also called refined Gross-Prasad conjecture, and this is the global analog of the theorem of Valls-Purgé I mentioned this morning. So the situation is similar. We start with two quadratic spaces of dimension n and n plus 1 over k. And then the groups are also the same. So H is the special orthogonal group of W, and G is the product of the special orthogonal groups of W and V. Okay. And so what kind of ingredients do we need? Now we need basically first a cuspidal automorphic representation for G. And then we have two other ingredients. One is the global period, so call it a Gross-Prasad period. Obtained, so again, it's the period integral over the subgroup H, so it's the linear form sending a cos form phi in the space of pi to its integral over H. And the other main ingredient is L function. So, and more precisely, we'll need the Rankin-Selberg L function. And we just denote by L as pi. So remark that pi is the automorphic representation of G, which is a product of two special orthogonal groups, and as such, it will decompose as an exterior tensor product of cuspidal automorphic representations pi W and pi V of the two factors. And this Rankin-Selberg L function is the tensor product L function. Or if you prefer, it's the more usual Rankin-Selberg L function of some functorial lift of pi V and pi W so these are the functorial lift to some general linear groups. So using the, these are particular cases of functoriality associated to the natural morphisms from the dual group of SOV and SOW into general linear groups that I used already this morning also. And we also need an adjoint L function. So which is, this is a particular case of L function, which is associated to the adjoint representation of the L group. Right? So this is the adjoint action on the Lie algebra of G hat. Okay, so now I can state the conjecture. So-called refined Gross-Prasad conjecture. So you have to assume something about pi actually. So assume that pi lies in a generic packet. Or in other words, so it's equivalent to say that the lift, the functorial lift pi WGL and pi VGL are generic as representations of general linear groups. Then, if you take phi in the space of pi, which decomposes as a pure tensor of local vectors phi v, the square of the module of this period should be, so the formula says that it should be roughly equal to an expression of the following kind. So let me explain all the terms here. And this is not exactly the expected equality. Actually, I am adding some local, some abelian L functions. But I will not bother writing the full formula here. But apart from this, the other ingredients are the following ones. So I will start from right to left. So first we have the local ingredients. So S is a finite set of places sufficiently large. And the PHV is a sesquilinear form on the local component pi v, which is the one we saw this morning. It's given by integrating over the local points of H, the corresponding matrix coefficient. And last but not least, okay, and these are partial L functions outside this finite set S. S pi is, and I will put this into quotation marks, should be the centralizer of the global Langlands parameter of pi. So it should be a morphism from Langlands hypothetical dual group to LG. It does not exist in general, but anyway, we can still make sense of S pi. So using the functorial lift to general linear groups, there's a way to define a replacement for this. And this is always a finite group, which is two torsion. And that's the conjecture. So let me make some remarks about this. You see what? So some important remarks. So the first one is why it is independent on the finite set S we have chosen. And actually this follows from an ramified computation. So that actually this local period PHV are equal, again, up to some abelian L factors that I will not write, to exactly the same quotient of local L factors as we see here globally. So that the product is really independent of S, provided S is sufficiently large. So this is for almost all V, of course. So more precisely, when everything is ramified in some precise sense. And so it doesn't depend on S, and actually can even be rewritten in a more suggestive, although not only formal way, as saying that the square of the module of the global period is up to this inverse of the cardinality of the component group, or centralizer, sorry. The product of all places, this time, of these local periods. But of course, this is not convergent because these points are outside the range of convergence of the Euler products for the corresponding L functions. So let me just put a prime. But so in some sense, you have to make sense of this product in the sense of L function. So it has to be regularized in the sense of L functions, right? Meaning that you have to replace formally the product of local L factors at a point where it does not converge by the corresponding evaluation of the global L function. And it's, okay, apart from this, then it looks much simpler. And we will follow this, this convention of writing products that does not really converge in what follows. And always it will be interpreted in this sense, actually. Okay. So another remark is that this conjecture is known in some cases. So it's known for n equals 2. It's essentially the formula of Valls-Purgé I mentioned at the very beginning of the first talk. Then for n equals 3, this is a theorem of Ichino on a triple product L function. And not much is known in higher rank. There is some partial results on some endoscopic cases for n equals 4, which are due to Wittek-Gann and Atsushi-Ichino. But otherwise, in higher rank, it's widely open, and it was mentioned also in the talk of Erez. Also, there is a similar conjecture for unified groups, where the conjecture has been proven. But, right, so the main point of this. For n equals 3, n equals 3, yes. You have Garrett, Kudla, Harris. Yes. Who else? Watson, yes, of course. Okay, we will prove some particular cases of this formula. But the main point of this afternoon lecture will be to try to explain that such a formula is not particular to this situation, and that actually this should be a general phenomenon. But I will try to explain how to reinterpret some of the terms in general, right? And one of the main terms, I will start from this form of the formula, is to reinterpret these local periods, right? And try to find an analog in general. So one of the problems is that this integral of matrix coefficients locally usually that do not converge. So this doesn't make sense. And so the first question is how to interpret PHV in a more general setting. And this is to make the connection with what I discussed this morning. So this morning we saw already these local periods giving you, which were dual to certain relative characters that were appearing in the local Planck-Schrell decomposition for those spaces, right? So recall that PHB, so restricted, let's say, to some tempered irreducible representation by V, was dual in some precise sense to relative character. G pi V, so we call that these are scalar products on the local Schwarz spaces. So where X here is G mod H, appearing in the Planck-Schrell decomposition. Or in the Planck-Schrell formula, rather. For this space, and this was because this space was strongly tempered, that we had this simple description of those relative characters as using integral of matrix coefficients, right? And so the idea of, which is due to Sakellarides and Venkatesh, is that, so first, let me restate the Ichino-Ikeda conjecture. Using those relative characters instead of the local periods, because this is what we will use afterwards. And also, this is to make the connection with the theta series I introduced in the first lecture. So recall that I said that if you take two global Schwarz functions, there is also a dual object to the periods, which are the theta series made of these Schwarz functions. And we have two theta functions. We can take the orthogonal projections to pi, and we say that this is exactly the dual of restricting the global automorphic period to pi. So this one means orthogonal projection to pi. And these are elements in the space of pi. In particular, we can take the Petersen inner product. And this should be equal to, this is exactly equivalent to the original conjecture. So the same global factor times a product of local relative characters, provided my test functions factorizes. Okay, and again, this product is not convergent and it has to be suitably interpreted in the sense of L functions. Okay. So we'll try to, under this form, it looks more generalizable because we saw this morning, at least conjecturally in the local setting, we always have local relative characters using the conjectural Planchard decomposition of Sakellarides and Venkatesh. But one point was that, maybe I didn't emphasize it sufficiently, but these spherical relative characters, even assuming the conjecture, are not canonical because there was also a measure, and it's only the product, or a spectral measure, or the product of these relative characters with the spectral measure that was canonical. So the first thing to define good local relative characters in general will be to normalize the spectral measure.
It's need some conditions on the the pi, right? We still need to assume this everywhere calculated.
Yeah, but let's not bother about it. Yeah. Otherwise, yeah, but it's still true for non. I mean, it's a conjecture, but conjecture is still true even if pi is not tempered everywhere. Just you have to interpret this also suitably.
So what is the subscript at 1 pi?
It stands for the Petersen inner product. So it's L2 product of GA mod GK. Okay, so my second topic now will be to explain how to normalize the relative characters locally. And as I said, it boils down to finding a canonical spectral measure. So the setting will be as this morning. So X is spherical. And there is a group G acting. Quasi-affine. Okay, plus some other assumptions, invariant. There is an invariant measure on Xk. This is a simplifying assumption. And more importantly, no root of type n. So that there is a dual group. And okay, for just this section, we'll assume K to be local, but we'll return to the global setting soon. So I also recall the local Sakellarides Venkatesh conjecture is saying that, and for the moment I will mostly ignore forms, inner forms, pure inner forms. So just one L2 of xk should decompose naturally as a direct integral indexed by the tempered parameters valued in the L group of X of certain packets. Maybe I should call them. Actually, I should have denoted them like this. It's better. So these are so-called X packets, if you want, times a spectral measure. Right? And this is also, I mean, what's behind this formula is a decomposition of the L2 inner product of two Schwarz functions on Sk as an integral of relative characters. So these are the relative characters. And these are the one we want for to state a global conjecture. And for this, we'll try to normalize this one. Right? It turns out that there is a natural candidate for this measure. And comes from the work of Iraga, Ichino, Ikeda in some sense. So let me call it like this. Because, okay, here is the idea. So roughly speaking, we would like to take for this measure the Plancherel measure for another group where Gx is a group of a K, let's say quasi-split, connected reductive, whose L group is the same as the L group of X, at least up to, I mean, if you renormalize the Galois action to fix a pinning. It's very natural because this set of tempered Langlands parameters, after all, they are supposed from the beginning, from the original local Langlands conjecture to parameterize tempered representations of that group. And that is a measure on the set of tempered representations of Gx. Right. The only issue is that this is not really bijection, so there are some packets. And so let me, okay. But roughly speaking, this conjecture of Iraga, Ichino, Ikeda plus a conjecture of Langlands will tell you that this measure can be described more or less using Langlands parameters. So the thing is that first we need some basic measure, natural measure to compare with. And there exists one. On the set of all tempered representations, this is the one which is given by, so roughly, this is R measure on families of generalized principal series of this form, where P is a parabolic subgroup with Levy decomposition mu, and lambda is varying over the set of unramified, how do I write it? And unitary characters of M. So, I mean that the set of all tempered irreducible representations of Gx can be naturally decomposed into such families, and such a family is essentially the same in canonical bijection with this modulo the choice of a base point, and modulo also the ambiguity that two such induced representation might be isomorphic or contain more than one irreducible representation. But more or less, these are indexed by unitary and ramified representations of M, and this is a compact group. And you can fix the R measure there. I will not say exactly how you fix the R measure, but there's a way to normalize those. And this will give rise to a natural measure on this. Right. But this is not exactly the measure we will use. Rather, we would like to use really the Plancherel measure. And the Plancherel measure will be absolutely continuous with respect to this one. And the conjecture, so it's due to, this is a combination of conjecture of Iraga, Ichino, Ikeda on formal degrees, and of Langlands on normalization of standard entertaining operators, is that actually the Plancherel measure on Gx is, so it's essentially, let me write like this. So you take the adjoint gamma factor of the Langlands parameter of pi times d pi. So this is the adjoint gamma factor. So this is essentially the ratio of two L factors, one at 0, one at 1, times some root number. And it has to be slightly regularized because it might vanish at 0. So you take actually the first non-zero coefficient in the Taylor expansion. And then there is some term So this only depends on the packet of pi. And then there is this term, where on the numerator you have so on the denominator first you have the cardinality of the component group of the centralizer of the Langlands parameter. And on the numerator you have the value at 1 of the corresponding character of this centralizer associated to pi, which is just the dimension of the corresponding representation, right? So you see that this measure is essentially descends to a measure on the space of Langlands parameters, except for this term, which might depend on pi, but all the other terms here only depend on the Langlands parameter. So let me put phi pi here. Right.
What is gamma? What is gamma?
Gamma is a gamma factor. So. Let's see. Yeah. And then there's epsilon factor. And also I'm adding the fact that it depends on the choice of additive character, this root number. But okay, let me just not machine it. It's also needed if you want a precise statement. You also have to normalize other measures, like measure on groups, and you have to use this standard. Okay. And so it tells us that indeed the Plancherel measure on Gx does descend to a measure on the set of Langlands parameters up to this small factor, which is bracket P1, right? And we'll take so for the measure of mu, this, so the gamma factor, absolute value divided by the cardinality of the centralizer times the analog of this canonical measure d pi, but for the space of Langlands parameters. So this is a measure on the set or the space of all tempered Langlands parameters for x. And maybe I will take but x there. So this will be the canonical normalization of the Plancherel measure. And as explained before, this gives rise now to a normalized relative characters. Gx phi, which are the one appearing in the Plancherel formula, which is here, here, on the top board on the left, when we use for a spectral measure this one. And of course, a priori, these are only well defined almost everywhere. And we make an assumption now. So this is for almost all phi. And the assumption is that there is a nice extension to all phi, namely this map extends in some precise sense. So, and this is true in all examples that can be worked out meromorphically to the space of all Langlands parameters. So that, in particular, we can now make sense of it for all phi tempered, where also I should say that it's more meromorphic, but there is no pole on the tempered subset. Okay. So now we have a kind of normalized related characters in general. And to get a global conjecture now, I mean, the global conjecture is still on the board, right? It's here. We would like to write something like this for general spherical variety. The problem is that this product will not converge in general. And we have to make sense, regularize it in the sense of L functions. So the first thing to check is if these local factors will give you some ratio of L factors at almost all places. And that's something which is currently, I mean, it's still a pending question in some sense. But let me explain what I mean by this exactly.
The concept will also be different in general, right? In the group case, it's 1. The scalar in front of the Euler product.
That I will come back to it later. Yeah. For the moment, I'm concentrating on this part, and then or maybe at the end we say something about this. Of course, yeah, we have also to find a suitable replacement for this endoscopic term somehow. Okay, so setting is the same as before, except that we go back to a global situation. We'll try to say something at almost all places, except so it's over K global that I will impose now, other than quasi-affineness, I will really impose the affine, that this variety is affine. And because, so I will try to explain, but it's not, it turns out that in all examples that have been worked out, this is the local factors will give you ratio of L functions only, I mean, this is usually under this assumption only. Okay, and to simplify, I will also assume that G is split. And because first I have to tell you what it means to do an ramified computation, right? So G split, and we fix a Borel subgroup with the unipotent radical denoted by n, as always. And to simplify matters, I will also fix a maximal torus A in the Borel B. And recall that we have associated to X a certain parabolic, standard parabolic, Px.
Is this an assumption or a conjecture?
It's a conjecture, but we'll take it as an assumption.
Okay, you expect it to always.
Yes, but as I said, it's really, I mean, okay. When you can, yeah, it's expected to be conjugal. Right, and we have this parabolic Px, and this Levy decomposition will induce one for Px also. And before telling you what's the ramified computation, so ramified computation will be a computation of these relative characters when these two test functions are what you think these are. But now I should tell you what it should be pi v here, right? So, and this comes from the most continuous part of the spectrum of X in some sense. So let's see. Yeah, I think I will be a bit quick on this, but that's the theorem of, again, Zacharias and Venkatesh, that the most continuous part of the spectrum, so in some measurable and quantitative sense, is so described as the direct integral indexed by, so it's, if you remember the local conjecture, which I think is not on the board anymore, there, it's there. And you look at it, so the most continuous part of the spectrum should be parameterized by those tempered parameters for Lx, which go into the maximal torus, right? So, and indeed there is such a summand in L2. So it's indexed by the unitary characters of Ax. mod Wx. And what I didn't say, so recall that Ax was a quotient of B, natural way. But actually, Px can also be defined under this quasi-affine assumption as the maximal parabolic subgroup containing B, such that Ax, this extends to a quotient like this. Right? And so this character chi can be seen as characters of Px, or Lx if you prefer, and now you take the normalized parabolic induction. XKV. And moreover, so let me give a name to this, like L2 of XKV empty. So by definition, this is this segment. So there is such an isometry. It's an embedding of this direct integral into this L2 space. And oh, sorry, it's Px bar. It is the most continuous part of the spectrum. Again, so it's a rather informal statement, but it can be made precise. And it should correspond in the local conjecture to the part corresponding to parameters which factors through the maximal torus. Yeah. And roughly speaking, the unramified computation corresponds to computing the relative characters associated to this part of the spectrum when everything is unramified. So more precisely, so circularities are also prove that under extra assumptions, but that are supposed to be to hold at almost all places. If you take the spherical vectors in this L2 space, this is included in this most continuous part, right? So in particular, we'll get for spherical functions decomposition of the L2 norm, let's say compactly supported, as an integral index. So this time only the unramified one will contribute, because otherwise they don't have any spherical vectors. And these are parameterized by unramified unitary characters of Ax. And these are the same as elements of the maximal compact subgroup of the dual torus, right? Yeah. And as we say, we not take the R measure. This is what we said before, but rather this canonical measure we defined before. And when you specialize to unramified parameters, it just gives you this. And now the goal is to see if this can give you a function when you plug so this is the when you plug the basic function here. And so this is the general expectation, and then I will try to state a formal conjecture, something like this, that if you apply these relative characters, unramified relative characters to the characteristic function of the integral points, then this should be a ratio of L factors. No, if you remove this, then it's L factor, but if you put this, the adjunct and the denominator. I think, right? This is the veil discriminant, but.
Can you clarify which adjoint it is?
Ah, yeah, yeah, sorry. It was written that way in my notes. So here add x, yeah, sorry. It's really the adjoint representation of Lx, right? And not of G.
Modulo de torus.
Yes, modulo de torus. I mean, yeah, modulo de. It's regularized, yes, you're right. I didn't regularize. Yes. Because this is always, when you, this is an abelian parameter, so it's always acting trivially on the Lie algebra of the torus. And otherwise, it would have a pole. This one will vanish. This will have a pole, so it will vanish.
Notation is fine.
Ah, okay. Okay, so let me state this as some conjecture that there exists a representation that will denote rho x of the A group of X in some complex vector space Vx, where, so I should emphasize that really here we should use for Lx the veil form. I will explain in one moment why. Or maybe the C group is better actually. Such that for almost all V, this expression is equal to so the value at 0 of the corresponding L function associated to so this is this unramified parameter divided by value at 1 of the adjoint L factor, again for x. And let me make right away one remark, which is that actually, so here I'm evaluating at 0, and you might say, okay, but in the Ichino-Ikeda conjecture, it was 1/2. Actually, this point of evaluation does not really matter, because we can always shift it by twisting this representation by an unramified character of the Val group. So that's why we need to use the Val group. But so the point of evaluation is a bit arbitrary. So it can always be changed by twisting by an unramified character. And experience shows that it's always an unramified twist by so there's always a shift by a half integer, and then up to this shift, this is just a representation with factors through a finite Galois quotient. So that maybe using the C group is better. Okay. So it's this conjecture is known in many particular cases from previous works on, in particular, through what are called unramified computations in the theory of zeta integrals. So, for example, there is the seminal work of Kassenman and Chalika on which you can see as a computation of this form. Okay, this is about Whittaker spherical functions. Then there is the work of Jacquet, Piasecki, Shapiro, and Chalika on Rankin-Selberg. Piasecki, Shapiro, sorry. And many other works actually. But so it was yeah already seen that this unramified computations sometimes give you L functions, L factors. Also, it wasn't phrased in this form using a Planchard decomposition. Okay, and let me give you two examples. So the group case. In this case. The representation rho x is just the adjoint representation of the dual group of H. And another one is the Whittaker case, which I said is a non-example of a spherical variety. But anyway, we can, with a suitable modification, make sense of almost everything. So x equals G mod n, but twisted by a generic character psi. Then the dual representation, well, there is no dual representation, just here. So there is no factor in the numerator. And somehow it's, the simplest case from the relative point of view is the Whittaker case, actually, not the group case. Okay. So let me now state some general results, and then we'll pass to the global conjecture. On what? There is some expectations. So as I will explain, in some cases we can describe the set of weights, and then there is still to say what is the representation, to show that there is really a representation of x hat behind. But and there are other other expectations about certain particular properties of Vx. For example, it should always be self-dual. But I don't know about a general recipe, like a conceptual recipe to tell you what Vx is. Okay.
One can cook up some conjectural recipe.
Yeah, but you will talk about it, right?
Okay.
And Akshay will talk about it. Yeah, okay. But I don't know about myself about the general recipe.
Read the recipe, not only examples.
Yes.
So answer of Yanis is yes. Okay. So there are some theorems showing that this is true indeed in some cases, or at least partial results in that direction. So the first theorem is due to Sakellarides. So it was done by direct, some sense direct computation, but by relating this to certain, the geometry of the spherical variety. And it is under some extra assumptions that, so G is split, I already assumed G is split, but X homogeneous and affine as before, plus some other extra assumptions that, well, at least most of them are supposed to hold in general, but let me not worry about. Then there exists not necessarily a representation of the dual group, but at least a representation of the maximal torus, such that we have the expected relation, but with rho t instead of rho x. And moreover, in this case, the set of weights, then the obvious question would be, does this representation of the maximal torus extend to a representation of Lx? And this is a question about checking if the set of weights is the set of weights of an irreducible representation, right? And we can describe explicitly a set of weights in terms of the geometry of the variety. This is given by the translate by the Val group of X of a certain finite set associated to elements D that are called the colors. So D runs over all the colors, which are B-stable divisors in X. And V check D, well, it should be a weight for the dual group, right? And it's just the valuation associated to this divisor, but that you restrict to the group of B eigenfunctions on X. And recall that it projects to the character group of AX, right? And actually, this will factor through this because the kernel is just the constants. And so this is an element in the co-character group of AX, or what's the same, a weight for the dual group. So character of AX hat. Which one? Ah, X. It's always a adjunct. Okay. And here is another result of the same kind. Again, due to Sakellarides with joint work with Jonathan Wong, yes?
You want to explain why you took the veil group version of the your group? You want to say that this is not an zero, is it? Like the n value is not really a zero, right?
No, but I'm just talking about the weights restricted to AX art, right?
Yeah. But I mean, in the theorem, this is really an unfunctional zero because you wanted to make a comment before about the.
Yeah, but I made it right. I said the point of evaluation is arbitrary. You can always twist. So there is really the draw action is non-trivial and it's encoding the point of evaluation. But maybe I should have said it more clearly. So really, it's why I didn't take AX art here. So it's encoding this plus some characters twist. Okay, and so in the work of Sakalaridis and Jonathan Wong, so it's a very recent work where the assumptions are the same as before, except that now the dual group, so not the same as before. So X is not homogeneous, so that's the point. But the dual group of X is the dual group of G, which is still covering most of the most interesting cases. And the characteristic of K is 0, so because I use some geometry of arc spaces to show that there is also a representation of the group of AX in this case, such that this holds the same identity. And they even show more because they show that the set of weights of this rho T also, this is, I cannot give you, there is some way to describe them, but it has a very nice structure, so it's not far from being the weights of a representation of X art. But also we don't know it in general, but the weights have the structure, a natural structure of what's called a Kashiwara crystal, which is kind of modeling what should be the action of lowering and what's the other? Okay. Actions of simple image of SL2 of the elements in the pinning, let's say, on the representation on the canonical basis. Okay, so let me now not lose too much time and try to formulate at least some global conjecture or global expectations. So it looks like we are all have the ingredients needed to formulate the generalization of Ichino-Ikeda conjecture. So let me recall the setting again very quickly. So you have X on which G is acting. This is smooth, affine, spherical, and over K, which is global. And I will formulate everything again by dualizing and passing to theta series rather than talking about periods. So recall that we have this theta series map that I defined in the first lecture, sending a test function here to its theta series theta f. And we will assume conjecture A, namely that the local unramified relative characters gives you a factor of ratio of L factors. So in particular, it gives rise to a representation of the group of X. Okay, and I will also have to assume for simplicity, but in some case, probably you don't want to assume this in general, like that there is a global existence of global Langlands parameters. So more precisely, if you take automorphic representation of G, we'll assume that we can associate to it a global L parameter, or more precisely a global Arthur parameter, psi pi, which is a morphism from the hypothetical Langlands dual group of K times SL2 into L of G.
The context now is global.
Everything is global.
Local before.
Here it was, but actually it was global, but I was putting V's everywhere. And because it was something which should be true at almost all places. And now, really global. Okay. So expectation, and this is again due to Sakellarides and Venkatesh. So first we will restrict to cuspidal representation in order to avoid analytic issues. Then we'll have to assume that actually we know now that some cuspidal representations are more degenerate than they should. And so we'll have to assume that pi is as tempered as possible, meaning that, so we have also, I recall here, the morphisms between the dual group, but this includes the SL2 part. So we will assume many things. But first, we'll assume that the restriction of the global Arthur parameter of pi to this SL2 is the restriction of iota x to SL2. So in some sense, pi is as tempered as possible for it to be x distinguished in some sense. So we'll only talk about the most tempered part of the X spectrum. And then there is also some stability issue. Right? And as Yanis mentioned, the naive analog of the Ichino-Ikeda conjecture and the group case do not work because of the global factor is not just 1 over the cardinality of the centralizer. And so to make life easier, I will assume that everything is stable from the beginning. So I will impose a stability condition. So I think we can either impose. So there are 2 ways to impose this stability condition. So either we can ask pi not to be not endoscopic. So the centralizer of C pi is trivial, let's say. Or we can ask the relative trace formula for x to be already stable. So it should be say something like this, that if you take a union over all the pure uniforms as defined this morning, and so the trace formula is essentially a distribution on those quotients, right? Whatever it means. And you can map this to the GIT quotient. Let's see. And what we would like is to avoid the existence of orbits which are the same over the algebraic closure but not over the base field. So we'll assume that this map is 1-to-1 generically. So some condition like this. Okay. Then we can write something analog. So again, I will take the projections to orthogonal projections to pi of my 2 theta series. Yes, you can see it like this. Maybe yeah, I have to be. Actually, I'm thinking now maybe it's not a good idea to take union over all pure uniforms, but yeah, this is a condition. At least it's enough. Okay, this is what happens in the Gross-Prasad case, but in the group case, then it will not be good for GL. No, okay, let's not worry. So, but some stability condition of that sort. So you take 2 theta series, project to the pi to pi and take the Petersen inner product, then it should be equal to not a product, so because we have again some multiplicities, but a sum over all global Langlands parameter in Lx, such that when you take the associated Arthur parameter as this morning, which is just iota x composed with phi times the identity, you recover the Arthur parameter of pi. And for each of these, you will get a product, right? The same form. Where F1, F2 factors as local product of local test functions, and where this product again has to be interpreted in the sense of a function because okay, and that's possible thanks to conjecture A. Okay, let me just, or more generally, we we would expect some formula like this for the Peterson inner product of two theta series. But as I explained in the first lecture, this usually is divergent, and this needs to be regularized, but let's assume that there is such a regularization. So this is this is a relative trace formula story. So you have to regularize this. Sometimes it's regularizable in canonical way, sometimes it is not. But let's assume we have one, and that we are some stability condition, then they should decompose as in this morning for the L2 space as an integral over the space of tempered Langlands parameters valued in Lx of exactly the same thing. Okay, there's a measure here. So, and this is, but again, this is the most tempered part, right? Plus, so even in the group case for GLN, we will be missing, for example, the residual spectrum here. So, because this doesn't have, they don't have tempered parameters. So plus more tempered part. But this is a rough expectation. More tempered part?
Less tempered or not tempered?
No, less tempered, yes. Or more degenerate, yes, sorry.
But even in the group case, you have this discrete contribution, for example, to the radical, right? So
Yes.
that's the other thing.
Yes. Yeah, okay, other stuff. Yeah, okay. But these somehow are like elliptic parameters, so it's okay. Let's not talk about. Okay, we stop there. I think I already. Oh.
Any quick questions for Raphaël? Yeah, please.
So conjecture 8, is that supposed to apply only to characters, like L parameters that are marked?
So, can you say?
Was conjecture 8 supposed to only apply to L parameters that factor through max intervals?
Yes, because you have to, even if you have this norm, sorry. So the question is conjecture A, should conjecture A only applies to those parameters that are unramified?
Yeah. Well, so okay, I'm confused because you said J implies some B was an L factor by conjecture A.
No, I said that, yeah, when you have a global Langlands parameter, conjecturally, phi v is a restriction to, it's the local parameter. It should be unramified at almost all places. So this is a ratio of L factor of almost all places, and then you should interpret this product as a ratio of corresponding global partial L function.
Thank you.
Other questions? Okay, so let's take a quick toilet break, 5 minutes, I think.